Now we turn to the proof of the inequality. Cosine of theta is less than or equal to sine of theta over theta, which is in turn less than or equal to 1 for values of theta between minus pi over 2 and pi over 2. And this, of course, can only hold when it only makes sense when theta is not equal to 0, because as we mentioned earlier, sine of theta over theta is not defined when theta is equal to 0. And so, what's the idea of the proof? The idea is that we'll compare the areas of three triangles, one smaller than the next, and when we simplify things, we'll obtain the inequalities we want. So first, let's look at this particular triangle here inside the unit circle. So this is a circle of radius 1, center at the origin. And if we look at the triangle inside, we have angle theta, and we have this height here. If we look at the coordinates of that point, we know that the height here, so the y coordinate is sine of theta. So this whole thing, the height here is sine of theta. And what is the area of such a triangle? Its base, which is 1, to base, which is 1, times the height, all of that divided by 2. Next, well, actually this is not a triangle, but this is a section of a circle, and we know that the area of a section of a circle is proportional to the angle. For instance, if we're considering the total angle here, we're measuring everything in radians. So if we consider, say, pi, then we get pi r squared over 2. R here is equal to 1. Remember that we're in the unit circle. And if we get a quarter, then we get pi over 2 times pi over 4 theta r squared. And so we're always proportional to the to our angles. It's like theta over 2. So the sector here BOA is 1/2 the angle. So theta, remember, if we're considering the whole circle, would be 2 pi, so it will give us pi and times r squared times 1 squared in this case, because the radius of the circle is equal to 1. So we simply get 1/2 theta, or theta over 2. And the last thing we're going to compare here is a triangle which is bigger than both of these regions already considered. One is containing the other, and that's why we can conclude that the area is at least the area of the previous thing. So if you look at this sector here, this sector certainly contains this triangle here that will be missing. Well, how do we obtain this sector here? We add this piece over here. And so the area is certainly greater than or equal the area of this triangle. Okay. And last here is this area. So this is actually something that contains both the sector and the triangle inside the circle. So how do we compute the area here? The area of the triangle OAC will be equal to 1/2 again, the base, which is 1, times the height, which is tan of theta. How do we know this is tan of theta? Because we have the opposite side. This is a right angle here. And so we have the opposite side divided by 1 has to be equal to the tangent of theta. And so this area is bigger than the area of the sector and the area of the triangle at the beginning. Excuse me. So once we compare the three areas, we'll obtain sorry about that. We'll obtain the desired inequalities. So the area of the first triangle, if you remember, so thus we get or we see thus no, not collecting the above, but thus the area of the triangle OAE is less than or equal to the area of the sector BOA, which is then in turn less than or equal to the area of the bigger triangle, which we just saw, or the area of the triangle OAC. So therefore, the area of the first triangle, we computed it to be equal, and we saw that it was equal to 1/2 sine of theta. The area of the sector was 1/2 of theta, and then the area of the bigger triangle was 1/2 of tangent of theta, which is equal to 1/2 of sine of theta over cosine of theta. And these three inequalities are going to give us the desired inequality. So let's look at this inequality over here. So 1/2 theta is less than 1/2 sine theta over cosine theta. Since we're in between minus pi over 2 and pi over 2, cosine is positive. So if we multiply both sides by cosine, we get cosine. Well, we can first cancel out the 2's here, so we get cosine of theta times theta is less than or equal to sine of theta. Right? And if theta is positive, so if we just consider values of theta between 0 and pi over 2, we can conclude also that cosine of theta is less than or equal to sine of theta over theta. Okay, and okay, so this proves the first inequality when theta is between 0 and pi over 2, but we know that this function is even, and this one is an odd over odd function, so the resulting function is even, so this inequality also holds when theta is between pi over 2 and 0. So we have the first inequality now. And then the next thing is to show that this is actually less, the sine of theta over theta is less than or equal to 1, and for that we just look at the first inequality. So we go back here. 1/2 sine theta is less than or equal to 1/2 of theta, and reasoning similarly, using the first inequality, 1/2 of sine theta that's equal to 1 over theta, and again for values of theta in between pi over 2 and 0, we include again that sine of theta, we can cancel the 2's on both sides, and we can divide by theta without changing the the inequality here. So we have that, but also again this function here is even for the same reason that we explained before, and therefore this inequality holds true also when theta is in between minus pi over 2 and 0. Like before, we get the validity this inequality for all theta in between minus pi over 2 and 0 as well. So we have shown the two inequalities we wanted to show, and this is, this concludes this part of the section. So we derive a inequality involving sines and cosines. We use that together with the squeeze theorem to derive the limit of sine theta over theta and 1 minus cosine of theta over theta when theta approaches 0. Okay, and this this is the final missing piece in the computation behind the computation of that important limit, that those two important limits. In case you forgot, we are gonna use those two limits to compute the derivative of sine and of cosine. The derivative of a function will be defined as the instantaneous rate of change, which we discussed at the beginning of the semester, and as such will be computed as a limit, and this limits of sine theta over theta and 1 minus cosine over theta will appear in these computations. Now we'll turn to applying this limit to compute some related trigonometric limits. They will be derived as easy consequences of what we've just done. And I have to point out to certain pitfalls that may wait for you. So you need to avoid these things, and I'll point out some certain mistakes that are very common. But once you get the gist of it, I mean, those kinds of problems will be very easy. And those are typical examples of the first midterm questions involving trigonometric limits. Since you don't yet know techniques such as L'Hopital's rule, because we haven't even defined the derivative yet, the only way to proceed when computing these limits is using one of these two limits, so sine theta over theta or 1 minus cosine of theta over theta. Okay. And then at the end, I will go over some other applications of the squeeze theorem that perhaps, I mean, they're not nothing that we're gonna encounter very often, but I mean, you need to know them. I mean, they appear from time to time in exams.